Hello, this is section 4.3 on translation and partial fractions. So today we're going to be looking at this rule called the translation rule, which tells us what happens when we multiply our function by an exponential e to the at. And what does that do to the Laplace transform? So what it does is it translates the Laplace transform by taking this a and subtracting it from s. So wherever there's an s in the Laplace transform of f, we replace it with s minus a. So the idea is that if you have an s, then you're going to replace that with s minus a instead. Okay, so get rid of the s and put an s minus a there instead. So that's the idea of this translation rule. So let's do a few examples of this. So here we have the Laplace transform of the function t. So this is our f of t. And then we have the e to the 2t. So that's this term here. So the first thing we need to know is what is the Laplace transform of this function t. So we have the Laplace transform of t. If you look at the table of Laplace transforms, it's 1 over s squared. I should bring up my table of Laplace transforms here. Let's see. Okay, got my table open. All right, yeah, so the Laplace transform of t is 1 over s squared. Okay, so this translation rule tells us that we should replace this s here. We're going to replace it by s minus 2, right? So that's the number there in the exponential. So we're going to replace it by s minus 2. So we'll have that the Laplace transform of t e to the 2t is equal to 1 over s minus 2 squared. Okay. So that's how easy it is. That's what this translation rule does for us. So now it allows us to handle more advanced Laplace transforms because of this very simple rule. Okay. So let's do another example. So in this case, the Laplace transform of cosine 3t is going to be s over s squared plus 3 squared, which is 9. Okay, so that's our Laplace transform. And so that means that applying the translation rule, we replace the s here and here, we replace it with s minus 2. So in other words, we replace s with s plus 2. So we're going to have s plus 2 over s plus 2 squared plus 9. Okay. Okay, so fairly straightforward, I hope. Now, when going the other way, when you're thinking about getting the inverse Laplace transform, a good way to think of this translation rule is that you have some Laplace transform here where, everywhere you have this s minus a in all places. And you can then factor out an e to the at from this Laplace transform. And then we just need the inverse Laplace transform of the function f. So it's kind of like you're replacing the s minus a with s now. So it's going the other way. So you have an s minus a everywhere, and you replace that with an s. And when you do that, you need to factor out this e to the at term. So that's the idea. Factor out e to the at. So let's do a few examples of this. Okay, so first of all, we have this Laplace transform here. So we need to first factor the denominator, and we get s plus 2 squared. And now we see that we have, it's always going to be an s plus 2 everywhere. So this is kind of a simple example because it's just the one place. But because I have an s plus 2 here, I know that I can factor out an e to the 2t. Or no, it would be e to the minus 2t because it's a plus sign. So we'll factor out an e to the minus 2t, and that will give us our inverse Laplace transform. And also we're going to use the fact that the, well, let's do the factoring out first, and then we'll see if we can figure out what the rest of the inverse Laplace transform is. So I'm going to write the inverse Laplace transform as lowercase f of t. So this will be the inverse Laplace transform of this f of s, which is 1 over s plus 2 squared. And then by the translation rule, we factor out an e to the minus 2t, and then we're left with the inverse Laplace transform of, so replace the s plus 2 with s everywhere. And we get the inverse Laplace transform of 1 over s squared, and we know from before that that is equal to t. So therefore, f of t, so this term here, this is equal to t. So we get that the inverse Laplace transform is t e to the minus 2t. So that's our answer. Okay. All right, another example. So again, we need to factor the bottom, see what we get, and then we'll figure out how to use this translation rule to help us. So the top is just 3s plus 5, and then the denominator is going to be s, so I'm going to complete the squares. So s minus 3 squared, so that would give me s squared minus 6s plus 9, but I have plus 25. So if I take the 9 from the 25, that will leave me with 16. So that's how we can factor that bottom part. And now we see this s minus 3 term here, and that makes us think, maybe we can use the translation rule here to help us. Now, the important thing about this is, I guess we can see from the denominator that this is going to be like a cosine 4t, and it'll be a sine 4t as well. But we need to make sure that wherever there's an s, it's always in this form, s minus 3. But in the top, we just have an s. So what we'd like to do is somehow make this an s minus 3, and then we'll be able to use the translation rule. So let's do that now. So imagine that we replace this s with s minus 3. Now we have 3s, which is there, and we also have minus 9. Okay, and what we need in the end is plus 5. So what do we add to minus 9 in order to get plus 5? So that would be 14. So if you multiply this out, we get 3s, and then we get minus 9 plus 14. So minus 9 plus 14 is going to be 5. So it checks out. So it's always good you go forward and then just double check by doing the same thing backwards and make sure that it matches. And now we have the form that we want. So now let's apply our translation rule. So we have that f of t is the inverse Laplace transform of this thing. Well, maybe instead of writing that again, let's just use the translation rule directly. So it'll be a little bit easier. So when I write this out, I'm going to factor out the e to the 3t. So I'm going to put e to the 3t, so factor that out. And then I need times the inverse Laplace transform of what I get when I replace the s minus 3 with s. So I'm now getting 3s plus 14 over s squared plus 16. Okay. Okay, so now we need to compute the inverse Laplace transform of this part here. So this is going to end up splitting up into two terms. There'll be a cosine term and a sine term. So e to the 3t inverse Laplace transform of 3 times s over s squared plus 16. So this will be our cosine 4t term. And then we have, let's see, I'm just going to make a little bit more room. And then we need to have plus, I'm going to figure out what this number, well, I guess it's 14. So it's going to be 14. And then I just need to multiply and divide by something in order to get the right numerator. So what is the numerator that I want? So right now it would be 1. But what I need is if you look at the inverse, the Laplace transform of sine kt, or in our case, it would be sine 4t. So the Laplace transform of sine 4t is going to have 4 s squared plus 6 plus 4 squared. So it would be 4 over s squared plus 16. So that's what we need up here in the numerator. And so that means we have to divide by 4 here to make it equal. And then we get e to the 3t. Now we have 3 cosine 4t plus, and I'll simplify that. That's going to be 7 over 2 times sine 4t. Okay, so there it is. All right, so a little bit more work was involved because in order to do the translation rule, we had to make it so that this not just an s here, but an s minus 3 instead. Okay, so we needed to be able to move from s minus 3. We needed to switch that to an s. So we just make sure we have s minus 3 everywhere. Okay. So now on to the second topic of this section. It's on partial fractions. So we're going to look at more advanced use of partial fractions. We've covered some of this already in previous lectures, but just to formalize it a little bit, we've noticed that when we're solving a differential equation, that we always get the characteristic polynomial showing up. So it's the characteristic polynomial times x of s. And then we end up dividing both sides by that characteristic polynomial. So when I'm talking about repeated real roots, I am talking about roots of the characteristic polynomial, but that ends up corresponding to having a term like this in the denominator. So we have some kind of formula, x of s is equal to, something over, and then we have an s minus a to the n term, and then something here. And this thing on the bottom, this is the factored form of the characteristic polynomial. So if we have a term like this in our denominator, then how do we do the partial fractions for this term? So what we do is we have a number a1 over s minus a, and then a different number a2 over s minus a squared, and you keep going up. So you start with s minus a, then you have s minus a squared up to whatever this number is, n, up to s minus a to the n. And then we have a different coefficient in the numerator for each of those. So this is what we would add to our partial fractions in order to split this thing up here into a sum of things that look like this. Okay, so that's the first thing. Now, what if we have repeated complex roots? So for repeated complex roots of the characteristic polynomial, that corresponds to having a term like this in the denominator of our Laplace transform. So we have an s minus a squared plus b squared. So this corresponds to having the roots a plus or minus bi. So that's what the repeated complex roots are. So if we have repeated complex roots in our characteristic polynomial, that means that we'll have a term like this in the denominator, and it's repeated n times. So for each one, we do the following. So we start off with just this term by itself, and then we add another fraction with the same thing but squared, and we keep going all the way up to n. And in the numerator, we always have to give sort of two terms. There's an s term, and then there's a constant term. So we have these two terms appearing in each of the numerators. So this is what we would add to the partial fractions. Okay, so this is kind of a formal way to say it, but it's better to look at some examples of this. Okay, so let's look at this problem here. So I want to factor the numerator. So I get 1 over s squared times s minus 5. And by those rules for partial fractions, we have a repeated root of 0. That's what this term here represents. So we're going to have an a over s, and then b over s squared, and then c over s minus 5. Okay, so that's how we split up this into 3 different terms. And now we're going to solve for the ABC. So multiply both sides by the s squared minus s squared times s minus 5. And we get 1 equals a s times s squared minus 5, s times s minus 5, plus b times s minus 5, plus c times s squared. Okay, so I did some problems like this in office hours, and the technique that we use there is to first of all substitute s equals 0. So this will get rid of this term, and we'll be able to solve for b. And then we can substitute in s equals 5, and that will make this term 0. This term is 0, and we can solve for c. And then after we have b and c, then we'll look at the s squared terms, and this will allow us to figure out what a is. So let's start with s equals 0. We get 1 is equal to minus 5b. So b is equal to -1 over 5. Then we do s equals 5. That gives us 1 equals, let's see, I'll get 25 times c. So c is equal to 1 over 25. And now we'll look at the coefficients of s squared on both sides. So the coefficient of s squared on the left-hand side is 0. There's no s squareds over there. And then on the right, we have an s squared appearing here. So the coefficient of that is a. There's no s squareds there. And then we have the coefficient of c here. So in total, we get a plus c as the coefficient of s squared on the right-hand side. And since we know what c is, it's 1 over 25, we figure out that a must be minus 1 over 25. Okay, so therefore, f of s is equal to minus 1 over 25 times 1 over s minus 1 over 5 times 1 over s squared, and then plus 1 over 25 times 1 over s minus 5. Okay. So then using our table of Laplace transforms, this is going to be a 1, this will be t, and this is going to be e to the 5t. So we end up getting minus 1 over 25 times 1 minus 1 over 5 times t plus 1 over 25 times e to the 5t. Okay, so there we have it. So there's that's what happens when we have a term like this in the denominator, an s squared. It means that we have to do partial fractions like this for that s squared term. Okay, let's look at another example. So we'll factor this bottom term, and it looks like I can factor it thinking of the s to the 4th. It's kind of like an s squared. So yeah, okay, I see. So we get s squared plus 1 times s squared plus 4. Okay, so that's what we get there. Okay, so this is going to be a simple as plus b over s squared plus 1. So these are not repeated this time, so we just need to have a single term for each one. And then cs plus d over s squared plus 4. And then we multiply both sides by the denominator. S squared minus 2s is equal to as plus b times s squared plus 4 plus cs plus d times s squared plus 1. Okay, so we'll go through our process of eliminating this. So we want that to be 0. So we'll put s equals I in there to make that 0. And then we'll do the same thing over here. We'll put s equals 2i, and that will make that term 0. And then we'll be able to solve for a, b, c, d. Okay. So let's do s equals I. So on the left-hand side, we get -1 minus 2i. And then on the right-hand side, we're going to get ai plus b times -1 plus 4 is 3. Okay, so now we just match up the coefficients. So for the I terms here and here, we have -2 on the left, and on the right we have 3 times A. So we end up getting -2 is equal to 3A. And then for the real component, we have -1, oops, we have -1, and on the right we have 3B. So we have -1 is equal to 3B. So now we can solve for A and B. Let me put them over here. So A is equal to -2 over 3, and B is equal to -1 over 3. Okay, and now we'll do S equals 2I. On the left-hand side, we get -4 minus 4I. And on the right-hand side, we get 2CI plus D, and then -4 plus 1 is -3. Okay, so for the coefficient of I, we have -4 on the left-hand side, and on the right-hand side, we have -6C. And then for the real part, we have -4 on the left-hand side, and on the right-hand side, we have -3D. So therefore, C is equal to 2/3, and D is equal to 4 over 3. Okay, so now we have everything we need. So we can now write our transform out. So s squared plus 1, s squared plus 4. Okay, so we have f of s equals -2/3 s minus 1/3 over s squared plus 1 plus, let me just move this down, plus 2/3 s plus 4/3 over s squared plus 4. Okay, let's break this up a little bit. So on this term, we have 2/3 times s over s squared plus 1. And then we have minus 1/3 times 1 over s squared plus 1. And that's what we want in the numerator there. So this is going to be sine t, and this will be cosine t. And then for the other terms, we have plus 2/3 times s over s squared plus 4. Let's see if I can make a little bit more room here. And then we have plus 4/3, but we want the numerator to be 2. So we need to divide by 2, and that would give us 2/3. So notice that, just checking again, 2/3 times 2 is 4/3. So we've done the right thing. So now we can write down the inverse Laplace transform. We get -2/3 cosine t minus 1/3 sine t plus 2/3 cosine 2t plus 2/3 sine 2t. Okay. Okay, so the goal with these Laplace transforms is to solve initial value problems. So that's what we're sort of preparing ourselves for. So now we're going to look at solving this initial value problem. And the rule that we need are the following. So we need to know that the Laplace transform of x double prime is going to be x of s minus s x of 0 minus x prime of 0. So we have that rule there, and I'll just make that a little bit smaller, just kind of put it over here. And then the other one is going to be the Laplace transform of x prime is equal to x of s minus x of 0. Okay, so those are the two things we need. So let's put a box around those. Okay, so that's all we need. All right, so let's look at this first problem. So we're going to do the Laplace transform of both sides of this differential equation. So we're going to have this term first. So let's write this out. So we get x of, I forgot something actually. So I did make a mistake here. I should have checked. So in front of these terms here, we need an s squared and then an s in front here. So let's see if I can squeeze that in. So I need an s squared right there. And then I also need an s. And that will go right there. Okay, so those are the correct formulas now. All right. So this will be s squared x of s minus s x of 0 minus x prime of 0 plus, let's put that over here, 4 times s x of s minus x of 0 plus 8 x of s. And then on the right-hand side, we have 1 over s plus 1. That's the Laplace transform of e to the minus t. Okay, so these initial conditions are quite nice. It means all of this stuff here is just gone. So that's all gone. So we're left with s squared plus 4s plus 8 x of s is equal to 1 over s plus 1. Okay, so remember when I said that we always get the characteristic polynomial appearing here, right? So that's precisely the characteristic polynomial of that. So always kind of double check that what you have here is the characteristic polynomial of this differential equation. Okay, so now I'm going to move this to the other side, and maybe I'll factor it as well. So I have s plus 1, and then what is this factored? It's going to be, let's see, I guess we're going to complete the squares. Okay, I need more room here. So completing the squares, and then, so that'll give me a 4, but I have 8, so I need to add another 4. Like that. Okay, so now we'll do partial fractions. We have a over s plus 1, and we have bs plus c over s plus 2 squared plus 4. Okay. So multiply both sides by the denominator. We get 1 is equal to a times s plus 2 squared plus 4. And then we have bs plus c times s plus 1. Okay, so now let's solve for the a first. And we can do that by substituting s equals -1, and that will make this term 0. So we get 1 is equal to a times, so we have -1 squared. Oh no, we have 1 squared, which is 1, plus 4. So that means that a is equal to 1 over 5. And now to make this term 0, we would substitute the following. So if I set that equal to 0, I get -2 plus or minus, I'll just take the plus 2i. So that's what we would get. If you were to say this equals 0 and then solve for s, you would get this. It would be plus or minus 2i, but we can just use the plus, and that will allow us to solve for the b and the c. So on the left-hand side, we get 1, and then it'll be a times 0, and then we have b times -2 plus 2i plus c, and s plus 1, so that'll be -1 plus 2i. Okay, so let's expand this out a little bit. So we have -2b plus 2bi plus c, and then we're multiplying that times -1 plus 2i. And I guess the most straightforward thing is to just multiply this out. So we'll have 2b minus 2bi minus c. So that takes care of this -1 times this. And now I'm going to do the 2i times this. So that will give me minus 4bi minus 4b, because I squared is -1, plus 2ci. Okay, so now we just match up the real and the imaginary parts of this. I can see some things are going to combine together, so those will combine, and yeah, and these terms will combine as well. Let's do that before we move any further. So we get -2b minus 6bi, and then minus c, and then plus 2ci. Okay. Just double checking. Yeah, looks okay. Okay. I'm going to add a page here. Okay, great. So now on the left-hand side, we have the real part is 1. And on the right-hand side, the real part is this -2b minus c. So we get -2b minus c. And the imaginary part, we have 0 is equal to -6b plus 2c. Okay, so we end up getting this 2x2 linear system. And we need to solve this for the c and the b. So I'm going to use Kramer's rule. So this would correspond to this linear system, -2 minus 1 minus 6, 2, and then the right-hand side is 1, 0. So using Kramer's rule to solve this, I would get the determinant of 1, 0, minus 1, 2, and divided by the determinant of -2, -1, -6, and 2. And then for the c, it's the same thing, but now we put the right-hand side in the second column. that. So b is equal to 2, and then we have minus 4 plus 6, which is 2. So b is equal to 1. And the c is equal to 6 divided by 2. So c is equal to 3. Okay. So a is 1/5, and then now we have the b and the c. So our Laplace transform is going to be let's put that there, and let me just highlight, I'll highlight this stuff. So a equals 1/5, b is 1, b is 1, and c is 3. So we have 1/5 times 1 over s plus 1 plus s plus 3 over s plus 2 squared plus 4. Okay. And now, so this term, we know this is e to the minus t, but this term requires us to use translation because we have this s plus 2 squared here. And we need to make an s plus 2 up here as well. So let's do that. So s plus 2, but then it's actually s plus 3. So I just plus 1, and now 2 plus 1 is 3. So that's perfect. Okay, so then f of t is going to be 1 over 5 e to the minus t, and then plus, we're going to factor out the e to the minus 2t because it's plus 2. So we're actually doing s minus minus 2. So that's why I get it. I factor out an e to the minus 2t, and then that's multiplied by the inverse Laplace transform of s plus 1 over s squared plus 4. Okay, so just one more step to break this into 2 parts. So that's the cosine 2t. And then we need to have 2 over s squared plus 4. And that means we need to multiply by 1/2 there. So now we get our final answer, 1 over 5 e to the minus t plus e to the negative 2t times cosine 2t plus 1/2 sine 2t. Okay. All right. Let's do another one. So in this case, actually, we have x to the fourth derivative of x. So if you look at the table of Laplace transforms, they have a general formula for the nth derivative of a function. And it tells us that we should write s to the fourth x of s, and then we do minus s cubed x of 0 minus s squared x prime of 0 minus s times x of 0 oh, wait. oh, right. I'm going up in the derivatives. So x0, x prime, x double prime, and then finally x triple prime, right? And we do have all those values. So there's those 4 values. So we know what these are here. Okay, so the s starts out with s to the 4th, and then it just goes down each time. So s to the 4th, s cubed, s squared, s, and then finally 1. And on the other hand, these x of 0 terms, they go up. So starting with x of 0, then x prime, x double prime, x triple prime. So that's how to remember that expression there. Okay, so then plus 13. We have s squared, x of s, minus s, x of 0, minus x prime of 0, and then plus 36 x of s, and then the right-hand side is 0. So the Laplace transform of that is 0. Okay, so let's combine these terms together. So we have s to the 4th plus 13 s squared plus 36 times x of s. And then let's see what we have here. So some of these terms are going to go away. Maybe I will indicate that to make it a little bit easier. So this term is 0. This term here is 0. This is 0. So that goes away. And then what are we left with? So we're left with minus 2s squared plus 13. And then down here we have minus 2. But this is an easy thing to make a mistake on. So this will be minus 2, but don't forget, multiply by 13. So that will be 13 times minus 2. So that would be minus 26. And that's equal to 0. Okay, so now let's solve for x of s. And we have 2s squared. So this will be minus 13, but moving it to the other side, it becomes plus 13. And that will be over, let's factor this. Let's see. So I guess we're going to complete the squares. Wait, do we need to do that? Maybe not. Let me think. So 36 is I do have the right numbers here. Yeah. Okay. So 36 is going to be what? 6 times 6, but that would be 12. And what else could there be? 4 times 9. 4 times 9. Yeah, and then 4 plus 9 is 13. Okay, that's what it is. Okay. So this is s squared plus 4 times s squared plus 9. Yeah, okay. I knew there must be a nice factorization for this. Okay. So now the partial fractions for this is as plus b over s squared plus 4 plus cs plus d over s squared plus 9. Okay. Multiply both sides by the denominator. like that. Now we're going to make some, substitute in some complex numbers, imaginary numbers. So let's first substitute in 2i, and that will get rid of this term here. That will make that 0. So then on the left-hand side, we get 2 times minus 4. So that's minus 8 plus 13. And on the right-hand side, we have 2a I plus b, and then we have minus 4 plus 9. So let's simplify this. We have 5. 13 minus 8 is 5. And then over here we have 5 times 2ai, so we get 10ai plus 5b. And so we get 0 is equal to 10a, looking at the imaginary terms on both sides, and we get 5 is equal to 5b. So therefore we have a is equal to 0 and b is equal to 1. Okay. And now let's do the other term. So s equals to 3i. That will make this term here 0. So on the left we have 2 times minus 9. So it's minus 18 plus 13. And that's equal to 3ci plus d times minus 9 plus 4. Okay, so let's simplify this. So we have minus 5 on the left, and then on the right we have minus 27ci. Oh, I did that wrong. This is minus 5, right? So minus 5 times that. So minus 15 ci and then minus 5d. Okay, so then we have 0 equals minus 15c, looking at the imaginary terms, and then looking at the real part, we have minus 5 equals minus 5d. So then c is equal to 0 and d is equal to 1. Very nice. Okay, so what is our partial fraction? So we have 0, 1, 0, 1 for these a, b, c, d. So f of s is equal to 1 over s squared plus 4 plus 1 over s squared plus 9. Okay. Great. And this is going to be 1 over 2 times 2 over s squared plus 4. So that's going to be our sine 2t, and plus 1/3 times 3 over s squared plus 9. And that'll be sine 3t. So oh, I'm using f's everywhere. Did I make the same mistake up here? I did. Let me just fix that quickly. Okay, so switch that because we're solving a differential equation and we're solving for x of t. So that's x of t. So this is going to be 1 over 2 times sine 2t plus 1 over 3 sine 3t. Okay, and that's it. So thank you so much for watching, and see you in the next one. Bye. Okay, I'm back. I know I said goodbye, but I was looking over the work I did and I realized I made a mistake here. So when I took the determinant of this matrix here, actually that determinant is -4 -6, it's not +6. So it's -4 and then minus, because -6 times 1 is 6. So it's -4 -6. So it's -10. It's going to change things a little bit. So that's -10. And then this will also be -10 here as well. So that means that these values here are going to be -1/5 and then minus 3/5. Okay, so those are the values that we have here. Okay, so that means, oops, up here, this is going to be -1/5 s minus 3/5. It's kind of tight. Let's see, -3/5. Okay, so we can factor out the -1/5 here, and then that will give us s plus 3 in the numerator. And now I think everything works. I just needed to divide everything in this term. I needed to divide it by -5. So that's all I needed to do there. So then this will be -1/5 here, -1/5, and then finally -1/5 there. Okay, so now when I compare to this answer, it is now matching. Yes, perfect. Okay, so fix that. Okay, thanks. This is hopefully the real end. Bye.